You know, from the bounce in your running shoes to the suspension in your car, springs are literally everywhere, quietly doing all this work for us. But have you ever stopped to think about how they actually function? Well, today we're going to dive deep into the physics that makes it all possible, the work done by a spring. So let me ask you this. What does a pogo stick, a car suspension, and even a simple clicky pen have in common? Yeah, the answer is springs, obviously. But it goes so much deeper than that. You see, they all operate on this single, incredibly elegant principle that governs exactly how they push and pull. And that's the principle we're here to unravel today. And that principle? It's called Hooke's Law. This is the absolute cornerstone for understanding not just springs, but elasticity in all kinds of materials. It tells us, with amazing precision, exactly how much force a spring is going to exert when you stretch it or squash it. At the very heart of Hooke's law is this beautiful little equation. Fs equals negative k times x. Now, I know it looks simple, but trust me, every single piece here tells a crucial part of the story. So let's break it down piece by piece. So let's decode this thing. We're going to look at each character in the equation one by one, and we'll start with S. All right, Fers, this one's pretty straightforward. It's simply the force that the spring itself exerts. It's that push or that pull you feel when you compress it or stretch it out, and like any other force in physics, we measure this in newtons. Okay, next up we have K, the spring constant. Think of this as the spring's personality, It tells us exactly how stiff the spring is. A really high K value means you're dealing with a super stiff spring, something like you'd find in a car's suspension. A low K value, that's more like the tiny, gentle spring inside a ballpoint pen. And finally, we have X. This is the displacement, and this is a really crucial measurement. It's how far the spring has been stretched or compressed away from its equilibrium position. Its natural, chill, resting length. So here it is, your cheat sheet. Fs is the force in newtons, K is the stiffness in newtons per meter, and X is the displacement in meters. But the real key thing to lock in your brain is that K value. Big K, stiff spring. Small k, weak spring. Simple as that. Now, you might have noticed that little negative sign tucked away in the equation. It looks so small, so insignificant, right? Wrong! It is without a doubt the most important part of Hooke's law. That little dash tells us everything we need to know about how a spring behaves. See, that negative sign means the force is always directed opposite the displacement from equilibrium. What does that mean in plain English? It means the spring is always trying to get back to its original shape. If you pull it to the right, it pulls back to the left. If you push it to the left, it pushes back to the right. This is what physicists call a restoring force. It's always working to restore things back to normal. Okay, let's see this restoring force in action. We can do that by looking at the three distinct states of a spring. Visualizing these is going to make this whole concept click, I promise. All right, take a look at the image on the left. Here, the spring is in equilibrium. It's just hanging out, not stretched or compressed. So its displacement, x, is 0. And because of that, it's not exerting any force. Now look at the image on the right. We've compressed the spring. The displacement x is to the left, which we call negative. So what does our formula say? The force, Fs, has to be positive. It's pushing back to the right, trying to get back to equilibrium. This table just lays it all out perfectly. At equilibrium, x is 0, force is 0. No brainer. When you stretch it, the displacement x is positive, but the force Fs is negative. It's pulling back towards the center. When you compress it, x is negative, and the force Fs is positive. It's pushing back out. Do you see the pattern? The signs for displacement and force are always opposite. That's that negative sign doing its job. Okay, so we've got a really good handle on the force. But force is really just half the story. In physics, what we often really care about is how much work that force can do. This is the big question, right? It takes us from just looking at a static spring to a dynamic one. When this spring actually moves something, how on earth do we calculate the energy it's transferring? Well, here's the catch. We can't just use that simple old formula of work equals force times distance. And why not? Because the spring's force isn't constant. Think about it. The more you stretch it, the harder it pulls back. This changing, varying force means we need a slightly more powerful tool from our physics toolbox. And that tool is this integral. Now, don't let the squiggly line scare you. All it's really doing is adding up the tiny bits of work over the entire distance the spring moves.
And when you solve it, you get this much cleaner, much friendlier equation for work. W's. The beautiful part is, it only depends on the spring constant K, the spring's starting position xi, and its final position xf.
Theory is great, but let's make this stuff real. We're going to apply everything we've just learned to a sample problem and see how it all plays out. So here's our setup. We've got a 2-kilogram block sitting on an incline. It's attached to a spring with a stiffness, K, of 8 newtons per meter. The block starts from a standstill where the spring is unstretched, and then it slides half a meter down the incline. Our mission, should we choose to accept it, is to find the work done by the spring. And this slide gives us a perfect picture of what's happening. As that block slides down the incline, you can see the spring is going to stretch out. This means its displacement, x, is going to increase from 0 to some positive value. Now for the fun part. We just plug our numbers into that work formula we saw earlier. The initial position, xi, is 0, right? Because the spring starts unstretched. That means that whole first term, 1/2 kxi squared, just vanishes. It's 0. The final position, xf, is 0.5 meters. So we plug that in, along with our k value of 8, and we get our answer. And that answer is -1 joule. But wait, why negative? Well, think back. As the block moved down the incline, a positive displacement, the spring was being stretched and was pulling up the incline, exerting a negative force. The force and the displacement were in opposite directions, so the work done by the spring has to be negative. It all makes sense. And this brings us to our final and maybe most important insights. If the spring did -1 joule of work on the block, what does that really mean? It means 1 joule of energy was transferred from the block and is now stored in the spring. We call that potential energy. You see, work is just the transfer of energy. That energy isn't gone. It's now just waiting, coiled up inside that spring, ready to be unleashed. The real question is, what happens next?